Welcome to the hydraulic press channel. Today I tried to make a compilation that actually teaches you something about physics. And first thing that we are going to cover is our super popular submarine implosion video. So here we have pressure chamber that we can pressurize up to 300 bars, and that equals about 2 miles of depth inside of the ocean. And the submarine that we are going to test is going to be a scale model of the submarine that imploded on Titanic wreck. So it's going to be built from carbon fiber tube. This is much smaller, of course, but similar structure, just carbon fiber. And then the end caps are going to be machined from metal. They used titanium, but we are going to use steel because weight doesn't matter on this application. And then the whole thing is going to be glued together with special submarine glue. And here it is inside of the chamber, so let's see how much of pressure it can take. So that was around 850 meters or half a mile of depth, and the implosion is really fast, as you can see here. It's only just like 1 or 2 milliseconds. Here it starts, and now it's already ended. And this is even slower than on the real ocean, because when this breaks inside of the pressure chamber, the pressure gets already lower because we introduce a lot of air into the system. That doesn't happen on the ocean, but it fills with the speed of sound, so that's pretty fast underwater. Then something bit similar but bit different. We are going to crush vacuum chamber underwater, and this is great trick how you can make vacuum at home. Probably don't try this, but if you put small amount of water inside of the glass jar and leave the lid slightly open, and then you microwave it with lot of cool light effects, the water starts to boil, and then the boiling water is going to fill up the whole jar with steam. And then when you are pretty sure that it's full of steam, you open the microwave and quickly close the lid. And then you just wait it to cool down, and while it cools down, the pressure of the steam gets quite close to the vacuum inside of the jar. And now we're going to crush it and see what happens. Okay, it goes. This is about 2000 frames per second. Hey, that's super nice. Super nice. And then last thing with the pressure chamber for shits and giggles, styrofoam cup. These are pretty simple stuff, but it's still funny to see how it shrinks like that under the pressure. Then the most surprising ball bearing crush ever. We were playing with liquid nitrogen, so it makes things really cold, and usually they are much weaker when they are cold. But with the hardened steel balls, like ball bearings, the super cool temperature actually makes the hardening better, so it makes them stronger. Okay, it's a bit harder. What the hell? How it's so strong this time? It should be weaker. Cooling the hardened steel kind of finalizes the hardening process. It increases the martensite, that is the super hard crystal form of steel that you achieve by hardening, and cooling down the hardened part increases that even more. So it's kind of like last phase of the hardening that you can do. And it was super interesting because I didn't know that these things even exist, and it destroyed the tools, and the ball didn't explode, but it instead of that it got like bit like flat. I have never seen that. Usually these just explode into million pieces. And then we are going to do some experiments with high pressure fluids. This time we are not going to test what the pressure does to things, but instead we are going to find out what it is the effect when the pressure leaks through small hole or opening. And here you can see the effects on high pressure banana leak on watermelon. That's pretty good. And I think this was around like 500 bars, so a bit more than or like 2 or 3 times your typical pressure washer. So these were quite interesting results. And now we are going to keep the same pressure, but we are going to test paint against ballistic gelatin. And we have small amount of leather between this. So this is going to replicate injection injury that can happen when the like paint can or hose start to leak.
Oh no!
Oh, I think I was too fast with the high speed. I get so excited, but that looks pretty bad. Oh no, that's bad. That was pretty bad. I think that could be your leg or something. That's not optimal. And here you can see how little damage it does for your skin, the injection injury, but how devastating the effect is inside of your tissue. And these can be really dangerous because paint or hydraulic fluid, that's toxic. And the hydraulic fluid can be also really hot, so it can also burn you from inside. So stay away from pressurized hoses whenever you can. And if you think that you might got like injection injury, always go to hospital, because if you don't go to hospital, then you might lose your hand or leg or whatever, or even die. So these are really dangerous, even if they don't look much from outside. But here with the ballistic gelatin you can see like how terrifying it's inside. I think that these are most common with paint guns and hydraulic systems. And now we are going to demonstrate hydraulic hose failure. So we have made small damage to hydraulic hose with the grinder. And then we are going to pressurize it with the hydraulic press and the piston. And there's going to be same blue paint inside and leather between the ballistic gelatin and the hose. So let's see how bad is the damage from hose failure. That was pretty solid amount of pressure. Let's have a look on the high speed first. I think that was a lot of pressure. That was eventful. Okay, Hanna, come have a look. Here it goes. Oh my god.
It's almost going through the pop. Oh no. Oh.
Oh no.
Oh.
Okay, let's keep going with the liquids. This time we are going to crush water. So you might not know, but you can actually compress water in. You need a lot of force or pressure. And with this cylinder we can reach about 2000 bars. and that should compress the water around 8%. So that's quite a lot when you think it's water and it shouldn't compress, but it actually does. So let's see. Okay. Yeah, it comes up when you release the pressure. And I can only release about half of the pressure from here. But you clearly can crush water with hydraulic press. That's so crazy. That was so crazy. It actually gets crushed.
Yeah, it does.
That's super crazy. And after that, I got the idea to crush it even more, because here you can see the water phase diagram. There is the liquid, vapor and ice, but up there at like really high pressures there is also ice, no matter the temperature. So if we take room temperature water and just crush it really hard, we are going to turn it into ice, warm ice. So let's see how it goes. And here we go. Okay, it has been really close, but I think we made it. Let me explain. Here it is. It goes in and it starts to leak around 5,000 bars, and then it still keeps going down and the force increases until it hits the like large piece of steel. And here is the upper part zoomed in, and we wanna hit the 24 tons to like get I6. And here we can see that when it hits 26 tons, it still goes down like fractions of a like millimeter, or maybe like 1 or 2 millimeters before it stops on the big tool. So if we assume that the force sensor doesn't have any delay, then it was just on the border. But check this out. When it hits the roller bearing, it takes like at least 5 frames to start to increase the force on the actual display. So there has to be like 5 frames delay on the force sensor. So if we take that into account, then this definitely hit the 26 tons like before hitting the base plate, and with 26 tons it's 2 tons over the like limit of I6. So there was like 1/5 of a second conditions where water should be I6. So that's not much, but with my best knowledge today I can declare that we crushed water into rock. And I'm going to revisit that with better tools. I'm working on it. But the easier way to make ice by crushing it is to use snow. And this is actually how the glaciers are made. So on the like areas of the globe where it just snows and snows and snows, the snow piles get so high that the pressure of the snow crushes the snow under the more snow, and it crushes it so hard that it turns into ice. Of course, there's probably like something to do with a lot of time going on, but here we crushed snow with couple thousand bars, and it actually turns into snow. Hey, pretty nice. There was the bottom part after all. And the ice isn't like clear. It looks like same color as snow. But is it hard? Huh? Hey! Would you say, Anni, that is it ice or?
It's a hard question because it's like white ice.
Pretty hard. Just check if I do like this. I think it's a white ice. Definitely not snow anymore. Then this still keeps popping up on the requests. Crush non-Newtonian fluid. So here we are going to crush it, and there's going to be a small hole on the cylinder that is going to let it out. But we are going to go so fast that it tries to get hard. And we are going to measure the force that is needed to force the non-Newtonian liquid with relatively high speed out from the small hole. So this is like demonstration how much it can fight the pressure. And as you can see, it takes like couple 100 kilos. Okay, now we stopped. And now we are going again. And now it's like 700 kilos or close to the ton at the end. And that turned out to be 40 bars or like this amount of psi. I think I have the reading coming here soon. And after this, we decided to try with bit harder fluid, like more cornstarch and less water, and that's coming now. Okay. Okay, so now we need about quite much of pressure. I think we have to check the replay. I didn't catch that. I think it was like the bottom half, it was about 2 tons. Okay, then the last thing on this learn with the hydraulic press series. We have lot of different steel bridge designs. This was series like many years ago. We had weavers design bridges and then we tested them with the press. And these were laser cut from steel sheet. And I weighed the bridges and then measured the strength that they can take. And the score was the weight that they can support divided by their own mass. So enjoy the bridges. Hey, I think that this works now much better. I didn't see well from behind the cover, but this felt here. So I think now it's actually works how the designs are supposed to be working. And the maximum force, only 2 tons, so maybe this wasn't super strong design. Okay. About the same, and I have to say that I'm pretty surprised that these don't help on all of the cases, because I think on these pretty similar bridges did pretty similar results without the support. Looking strong. Oh. Yeah, it's gone. Oh. Yeah, it's gone. Okay. Looks good. Really solid. Oi! Oi! That was good result. Okay, that was 3.8 tons. I think that's much more than we got on the last time. Okay, so that was a bit over 1 ton. Okay, looks again really strong. Yeah. Okay, and the result was 2.8 tons. I think this is the second place probably. And that's also end of this Learn with the hydraulic press video. Thanks if you watched all the way here. And I'm going to probably start to pop out a couple of videos per week for this month. These compilations are great to get new viewers for the channel and get the newer viewers up to the speed with the channel. And then on every Saturday we are going to do completely new and exciting hydraulic press channel video, and I have really great videos planned for this month. So that is all for today. Thank you for watching and have a nice day.